Hey there, in this video we're talking about C strings and parallel arrays and the single biggest danger in all of programming, which is buffer overflows in C++. And this covers sections 7.6 to 7.7 or thereabouts in the Gaddis textbook. So we've been working with arrays for a couple days at this point and some other stuff, some other details you should know about them. In particular, this big problem that I've left until now. We'll talk about that in a couple minutes. So first of all, let's talk about strings. And C++ actually has two separate types of strings you can possibly use. Up until now, we've used this string object class that's been made for C++. You know, when you actually declare a variable of type string, which to my thinking is new to the C++ language. And here, just for a second, we're going to think about what happened in the prior language that's just called C that didn't have this string data type. And you know, anything that you could do in C, you can still do in C++ basically. So you will see this in C++ code sometimes, C strings. So in the C language, strings are simply null terminated character arrays. Okay, so hopefully that makes sense. I mean, what is a string? Fundamentally, it's just an array of characters. It's not really a brand new thing. It's a block of memory that just has a whole bunch of characters from start to finish. So in the C language, that's what you'd literally do. You wouldn't make a variable of type string, you'd make a character array. And that is how you would save all of your strings and names and things like that. Fortunately, here we are in C++. You can still do that, use a character array for a string, and you know, initializers, you know, with string literals, it works with that. Sin and count are know about C strings and will work automatically with that. And I like talking about it now because there's a bunch of legacy functions, a bunch of older functions in C++ that still expect to work on C strings, not C++ strings. And off the top of my head, I'm thinking command line arguments need C strings, binary files, writing structures to binary files need C strings. And that's all stuff we'll talk about in the future. But just to lay the groundwork for that, you know, what are strings really? They're arrays of characters. You want to see more of this. Actually, chapter 10 in the future is all about digging into the details of C strings. But I just wanted to mention a little bit right now. So here's an example of that. I'm making a character array. That's what's happening on the second line. Now, of course, in order to make that, we gave it a named, a labeled constant called maxchar. So a constant integer called maxchar for the maximum number of characters that you can put in your string here. And we don't have a string variable type. We're just making an array of type character, called it str for string, sized it to this maxchar, which is 25, and here we're using an initializer, setting it to this literal. So all those characters that you see in the quotes, that's actually what's in the character array to begin with, and that counts as a string. Don't forget, there's also a null terminator that comes right after that to tell C++ where the string ends. You don't actually see that. And then, you know, once you have that, you can just count out this string, this str, right? Technically, that's a whole bunch of stuff, a whole bunch of characters in an array, but C and C++ know that you want to handle that like it's a string, and that totally works. It prints out greeting to the screen. So again, two separate ways of handling strings, the C++ string class, or do it old style with a character array, because after all, that's what strings really are. They're a bunch of characters, one after the other in memory, and that's an array. That's actually going to be in the lab. So at the end of this particular session, the next lab we do has you entering names for students, and they're actually stored in arrays just like this. So be on the lookout for that. Okay, second thing. Up until now, our programs have only used one array at a time. But of course, you can have more than one array at a time. And if they are holding related data, these are called parallel arrays. Kind of like in my head, I'm thinking like, I've got a couple arrays now. Right next to each other in memory is the idea. So using two or more arrays with related data in matching index locations is referred to as parallel arrays. Now, let's say, for this example here, let's say I need to record names of employees, and also how much money they make. Now, in this case, I can make two separate arrays, one for all the names, which would be type string, and one which would be type double for all of the wage numbers. And remember, when you make one array, you can't mix and match types. It has to be just one type. So if you want that to happen, what we're doing is we're making two separate, totally different arrays. One for the names as strings, and one for the wages as doubles. And the important thing is that the entries at the same index have to refer to one person. So if I've got Alice in my company, the names array subscript 0 has got Alice's name in it, and the wages array subscript 0 has got her pay in it. And then maybe employee Bob is employee number 1. So names array subscript 1 has got Bob's name, and wages array number 1 has got Bob's wages. So whatever the subscript, wherever the index is in one array, has got to perfectly match with the other one, and you've got to keep track of that in parallel. So having said that, right, the only thing that makes sense for any example like that is these two arrays have to be the same size. I'm going to have the same, the number of employees, the same number of names is the number of wages that I've got to keep track. So that will cut down a little bit. I can just have one constant for the size of both arrays because they have to be the same size. And when I make a for loop to process them, I can just have one single integer counter that's going to handle both arrays because they have to match like that. Now, the risk of parallel arrays, it's a nice technique, but the risk is that if you fail to keep that index synced up, matching between the two arrays, you might put Alice's name in element number 0 and put her wages in element number, 5, right? And then it's mismatched and you've lost the connection to the data. So you do need to be a little bit careful, but as long as you just use one single counter for both, it's probably going to be the obvious thing to happen. I will say that in a later course, we'll actually have a better way of relating data like this. There's an idea called structures in C++ or classes, that it would be better to actually just put the name and the wage together and not possibly have it get disconnected like that. But for now, let's think about using parallel arrays to get started with. Here's an example of that, program 715 out of the book. And yeah, this program uses two parallel arrays, one for hours worked and one for the pay rate is what this example does. So declaring our data at the start of the main function. And of course, we're using a named constant called num employees for the number of employees, and that's being set to 5 here. So just one, right? Now on lines 10 and 11, we're declaring two separate arrays. On line 10, I've got an integer array called hours for the number of hours people worked, and that's sized to 5. And on line 11, second array here, I'm making a double array called pay rate for their wages, and that's also sized to 5. See, those have to match like that. So one single constant for the size of both arrays. Now, here comes the input part. So we're going to be getting the data for both arrays at once with one single for loop. So here we're inputting the hours worked and the hourly pay rate. You get a prompt, enter the hours worked by 5 employees and their hourly pay rates. So one single for loop, one single counter called index. It's going to go from 0 to num employees, of course. And inside that one for loop, I've got a prompt for the hours worked by employee number, whatever, right? And that gets put in hours subscript index. And then there's a prompt for the hourly pay rate for that same employee. And that number goes into pay rate subscript index. So you notice on lines 20 and 22, we had to make sure that index is the same number. And of course it is. So as you go through this for loop, index will be 0, and then 1, and then 2. And all the data is being put in matching locations in the two arrays. So the fact that they have to match like that, mentally we're thinking they're running next to each other, they're the same size, and that's why we think of these as parallel arrays. Now obviously that's just the input part. So here's the end of that program. They're going to compute the gross pay, which is the product, the multiplier of the number of hours worked and pay rate, print it out to the screen. So here's the gross pay for each employee. Set up, this is money, so we're going to be printing to 2 decimal places, so we do that. And of course, processing arrays, here's a for loop. So another for loop with one single counter index, counting from 0 to num employees. And for each separate employee, we're computing their gross pay on line 30. We're multiplying hours subscript index times pay rate subscript, the same index. And again, it was really important on line 30 that we had the same index in both sets of square brackets. If those had been different, maybe I'd be multiplying Alice's hours worked times Bob's pay rate, and that doesn't make any sense at all. That would be broken. So really important that we had one single variable and we used the same index in both of those sets of square brackets. Now, once you have a legitimate gross pay, now of course you can print out employee number, whatever, here's your gross pay, and that will actually be correct. And here is our example of parallel arrays in the IDE at this point. And I think with this program, I just want to go right to the debugger and see what happens in memory when you run this program. So breakpoint, start the debugger. And I'll put some watches on important data like those arrays. So I have an array called hours. Got it. And I have an array called pay rate. Okay. And you can see they're both size 5. And of course, as the program starts up, they both have random garbage in them to begin with. Now, hours is an integer array. So you're seeing a bunch of random integers for that. Some big numbers, there's a -2 in there. Pay rate is a double array. And if you remember from earlier, we said that floating point data, like doubles, is actually stored internally like it's scientific notation. So what you're seeing here appear to be crazy random scientific notation numbers, starting with -1.150, bunch of stuff, times 10 to the 251st power. And there's 1.252047, bunch of stuff, times 10 to the -312th power, and on like that. So hopefully you agree these are good, truly random garbage scientific notation numbers that probably no one could guess. And that's what normally happens. Other thing, you notice that just when we put these in the debugger, these things look like they're parallel lines, right? You got one block for the hours and you got one block for the pay rate literally running in parallel. So I think that's kind of where this terminology comes from. A couple other pieces of data here. There's this index variable that controls the for loops. Hasn't been made yet, right? You haven't got down to that line where it's declared yet. And then there's also this gross pay variable that's going to show up later on. Not declared yet, but it will be there. So let's see what happens when we step through this. Okay, so here comes the prompt for the user to enter the hours worked by your 5 employees and their hourly pay rates. Now, this prompt kind of expects to have a larger console, right? It would look better like this, but I don't have space for all that stuff, so I have to kind of squeeze it over here right now. But the interesting stuff is here comes this for loop to control the input. And to begin with, index is going to get initialized to 0 instead of the random garbage it is right now. Okay, so index is 0 right there. And now you're going to get these prompts for the hours worked by employee number 1. And you can see that, just see that first prompt there. So you can see that when I type in a number here, it's going to get stored in hours sub 0, because that's what index is. And then right after that, I'm going to type in a number that's going to get stored in pay rate sub 0. So for this first employee, it's using the first slot in both arrays for their hours and their pay rate. And again, these things have to be in sync like that for things to work later on. So here comes my SYN statement. And let's say this employee worked 10 hours this week. Here comes the prompt for employee number 1's pay rate. And here's this SYN statement. And let's say that this employee is making $15 per hour. There we go. Okay, so you can see that the 10 and the 15 are stored in the first slot, the matching slots in the 2 arrays running in parallel. And then here for the next cycle, obviously, index will become 1 when this increment happens. No surprise there. So index is now 1. And so now you're seeing for the prompt, enter the hours worked by employee number 2. And when I type a number in here, like let's say they worked 15 hours this week, this is going to get saved in hours sub 1, because that's what index is, and the pay rate's going to get saved in pay rate sub 1, matching locations. So hit enter on this, and then here comes the prompt for the pay rate for employee number 2. Right, getting all the information about one employee at a time, and let's say they're making $20 an hour. Okay. Went back up to the for line, right? You can see the 15 and the 20 are in matching locations for employee number 2. And you can kind of see what's going to happen here. So I don't think we have to keep repeating this over and over again. I'm going to run this full speed for a second for the rest of the input. And I'm just going to put a pause down when we get to the beginning of the output. And I'll hit continue to kind of run this full speed. So here's what this normally looks like. Hours worked by employee number 3. Let's say they worked 30 hours and they're making $20 an hour. And employee number 4 worked a full 40 hours. They're making $15 an hour. And then employee number 5 worked 25 hours and they're making $20 an hour. Okay, so there's what the input normally looks like, full speed. Now we've paused this down here on the output phase as we get down here. So now it's going to print this label. Here is the gross pay for each employee. There we go. Here's the gross pay for each employee. You get into this new for loop, and again, it's going to recreate the index variable, set it to 0. You know, this is having a little bit of trouble here because this is actually a different variable. You can see there's a declaration up here for index that only exists inside this for loop. When you get to the end of this for loop, it gets scrubbed out of memory. This variable here is actually a different variable, and it's only going to live while we're working in this for loop. So the debugger is actually having a little bit of a trouble keeping track of the 2 separate variables with the same name. Maybe if I put the watch back up here, it'll know that I'm talking about the second variable here. So index is 0. And now when it does this calculation on line 30, notice that both of my arrays, right, running in parallel there, are filled out with legitimate data in matching locations. So it's going to look at hours sub 0, that's the 10, and pay rate sub 0, that's the 15, multiply those, which is correct because that's the information for the first employee. So I think that ought to come out to be 150, I think. Yeah, so there's gross pay 150, and now the printing happens, and it prints out employee number 1. You get $150. So there's all this printing happening there, and you can see that there. Yeah, employee number 1, their gross pay is $150, and that is correct. So now index gets incremented up to 1, and now you're matching hours sub 1 and pay rate sub 1, matching indices. So it's going to take the 15 and the 20, multiply those out, you'll get $300 for employee number 2. So there's the 300 in gross pay, and now the printing happens, and you see it in the console. Great. Okay, so I'll just kind of go through this a little bit faster. So then you multiply out the numbers for the gross pay for employee number 3, right there. And the next employee, that's the 40 times 15 is what's going to happen next, which ought to be well, that's actually, I guess that's this one. I guess that's also 600, I guess, is what it is. So here comes another 600. And then the last one is going to be 25 times 20, which ought to be, I think, 500, I think. Yeah, so there's gross pay 500, and that's what's getting printed out for the last employee. And the for loop is over. So there is the correct amount of money that should be paid for these 5 employees. Keeping the indices matched between each of the elements in these 2 parallel arrays, as you can actually see in the debug tab. And we're kind of cleaning things up here as the program finishes, and we're done. Nice. All right. Now, here is the subject that I've been warning you about, I've been alerting you to. Buffer overflows, the single biggest danger in all of programming. Single biggest risk, at least in C++ programming, probably all of programming at all. This is actually a little bit earlier in the book. I have delayed this conversation until now, so you didn't get too freaked out about it, frankly. But every C++ programmer really needs to be very aware of this super, super risky issue. So buffer overflows. Now, buffer is basically a synonym for array. It's a block of memory where you're going to save some stuff. You're going to write some information. So a buffer overflow is when you write data past the end of an array, go past the end of it, and therefore overwrite adjacent memory and wipe out some other data by accident. So the reason why this is even possible is that these slightly older languages where the programmers has total control, C and C++ do not record internally how big your array is, does not check that you've gone past the end of the array automatically. Newer languages like Java actually do this, right? So in Java, this is not as big a risk, but Java is a little bit slower because it's always got this like traffic cop kind of paying attention to make sure that data doesn't go in the wrong place. C and C++, because they're intended to be super fast, super optimized for controlling rockets or neural links or automatic cars or things like that, doesn't have this protection built in. The programmer has the responsibility of being aware not to make this hideous mistake. So in our languages that are super optimized for speed like this, the programmer must be careful to keep track of the size, for example, with a named constant. We've done that for all the arrays we've made, so that's using the named constant will keep us safe. Otherwise, if you glitch that up, your access may go past the end of the array, wind up in some other memory location, overwrite, trash, and erase other data in memory. And what data was there, I have no idea. It could be a password, it could be an age, it could be your name, it could be like somebody's payment, it could be anything. It could be a for loop controller. And as a result, any kind of crazy problem could possibly happen on the computer. The program could crash, other programs could crash. You could have memory leaks where parts of memory are no longer accessible. On a website, this creates hacking vulnerabilities where someone can take over your system by overwriting your memory. Bugs that are just super hard to track down and fix. So basically, anything's possible when you just start randomly trashing memory with a buffer overflow. And if I see a program that just acts totally maniacally crazy, just crazy stuff's being printed to the screen, it's totally unpredictable, I start thinking about a buffer overflow because that's what that looks like. It's just, when this happens, it's just super hideous and super hard to solve. So you really kind of want to avoid buffer overflows like the plague. They are the worst thing. So here's on the next slide, we're going to see an example in the book that's like the worst example they could possibly write that actually has a buffer overflow. And visually, here's what's going to happen. We're going to make an array called values that's size 3. And it's got integers. So each of the boxes in this picture is one integer in memory. It's really 4 bytes. It's going to be somewhere in the memory system. And there's some addresses that come before it, and there's some bytes that come after it, obviously. And we know that for an array size 3, the first subscript is 0, and then comes values 1, and then comes values 2, and that's the last one. There's your 3 things. So hypothetically, if you're writing or saving data and you glitch up your for loop that's going to do that, what this example actually has is a for loop that actually runs not 3 times, but 5 times. And so it tries to print a number, tries to write the number 100 to 5 locations. And that compiles, and C++ will totally do that. It's just really bad when it happens. So it'll write 100 to values 0 and values 1 and values 2, like you expect, that's fine. But it's also going to print the values 3 and also store 100 in values 4, which aren't actually part of the array that you made, but those have to be things that come after your array. And whatever used to be there, I don't know, your name, password, something else, something really important to Windows, just got overwritten with 100. And whatever data was there just got trashed. And I don't know what the result of that'll be. Possibly any possible crazy side effect. It'll be really bad. Maybe, or maybe nothing. Maybe we'll get lucky, right? Anything could happen. Let's see that. So here's this program 7.5. And this program unsafely accesses an area of memory by writing values beyond an array's boundary. And this is the only program in the entire book that's got this all capitals warning here. Warning, if you compile and run this program, it could crash. And they're definitely right about that. So here we are at the start of the main function, declaring an array size 3, of course. Has this named constant size here. And we're going to have some for loops, right? We're going to write information to the array, try to print it out again. And you notice the terrible mistake on line 15 is they wrote a literal number here for the for loop limit. They didn't use size, right? If we'd actually written size right here, that's 3, and then this program would be perfectly safe. But they didn't use the named label. Instead, they tried to write a number, and someone wrote down the wrong number. It should have been 3. They wrote down 5 instead. So here, this loop will actually try to store 100 in values sub 0, values 1, values 2, values 3, and values 4. But values 3 and 4 aren't really in our array. There's something else. They're right after it. So then we'll get down to this part, and it says if the program's still running, because it might have crashed when it tried to do line 16, we're going to try to display the numbers. And it's going to print out, if you see this message, it means the program has not crashed. Okay, I guess you get lucky in that case. Here are the numbers. And you have another for loop counting 5 times, and it tries to print out values sub 0 and 1, 2, 3, 4, even though 3, 4 aren't really in your array. And we'll see what possibly happens. Maybe you get 5 100s back. Maybe not, because if some other program was using those parts of the memory, then maybe that program came back through and overwrote our hundreds. I don't know. All kinds of stuff could happen. So I'm going to try to test this. And actually, I will say that this program right here, it makes me more uncomfortable than any other program in the book. But operating systems nowadays are fairly safe. I don't think I'm going to do anything too miserable to my computer. And, you know, the labs at our school are very safe, of course, so I'm happy to run that in the computer labs. But, you know, I actually, when I am running online classes, I actually do alert the students in advance, like if I lose the connection, you know, maybe my whole computer crashes when I run this. But we're gonna try this here now. Okay, so I have loaded up this super sketchy program 7.5 into my IDE, and I am going to compile it and run it, and I'm going to cross my fingers and hope that it doesn't blow up my computer. So compile it. Yep, okay. So of course C++ lets you do that, and I'm going to run it. And once again, kind of unclear. Could be a bunch of different things could possibly happen. Could be different on different runs. It's very unpredictable when you have a buffer overflow. But here we are writing 5 numbers where there's really only 3 locations. So we're going to be trashing some memory, and I don't know what's there. Let's see what happens. So, okay. So it says here I'm going to store 5 numbers in a 3-element array, and it did actually get down to line 19 in this case. So it printed out the, if you see this message, it means the program has not crashed. Here are the numbers. 100, 100, 100, 104. Isn't that interesting? So apparently this wrote 5 100s, but I guess the last location must be in use by Windows or another program or some system. And so between me writing and me printing, that my 100 got overwritten by somebody else's 4. So apparently there's 2 systems in conflict here for that 5th location. I lost my 100. So in this case, I'm the one losing data. And if it was important to record, 5 grades, this buffer overflow made me lose one of my pieces of data. That's not good. But, at least the program didn't crash. Okay. What am I going to do? How about I overwrite more memory? I'm going to make this program even worse. So instead of writing 5 numbers, I'm going to write 50 numbers and try to print 50 numbers out. So now I'm trashing more memory here. I'm going to recompile this, and let's see what happens now. Okay, that's pretty weird. That's very weird. So you can see that, where it's supposed to have printed, I will store 5 numbers in a 3-element array. It's not even making that visible. You're seeing some zeros get printed out and some big numbers. That's pretty crazy. Technically, the program didn't crash because I see it's got a return value of 0, like you're supposed to have at the end of the main function, indicating there's no errors back to Windows. But clearly, there's some errors happening here because I'm losing some of my printing statements, and I'm losing some of the data being printed. I don't see any 100s. So that's what we mean by being kind of crazy behavior. Let me try that again. I'm going to run the exact same program again and see if the same thing happens. So run this. Is that the exact same thing? Not exactly the same thing. See, previously we had some scattered zeros, and now I don't have any blank lines there, but I've got different numbers there. So I've got big numbers and negatives and a big string of zeros. I guess there's a gap there. But that's a different series of numbers being printed out than we saw before. It's the same code trying to do the same thing, but that's some crazy stuff happening. Let me run that again. Okay, so again, bunch of crazy numbers there. That does not look good. But the program's still not crashing. Let me make this even worse. It's already pretty crazy. Okay, so now I'm going to really trash some memory. I'm going to overwrite 500 integers worth of data. Let's see what happens now. Okay, well that's weird. Now it looks like I'm getting a whole bunch of hundreds. Okay, blank lines, blank lines. Here comes some hundreds. I guess those ones stuck around in memory. Bunch of blanks, I guess. Here's some more hundreds. Program still didn't crash, but it's gone, nutso with that. Let's make this really bad. You should probably not ever do what I'm doing right now. This is frankly a bad idea what I'm doing, but now I'm curious about how bad this can get. Okay, so now the program crashed. And you can see that this did the, I will store 5 numbers in a 3-element array that happens on line 14. It tried to print 5,100s when I don't really have authority to use that much space. And the program stopped working, and it did actually crash and never got down to line 19. Never got down to printing numbers back out. And you can see now the return value is not 0, like it's supposed to be. That's some kind of error code that maybe Windows actually detected what was happening, stepped in and terminated my program before really bad things happened. I guess I'm thankful that Windows did that, but this program did actually crash and was terminated before we ever got down to line 19. So there you go. So that's what can possibly happen. You can have some crazy stuff. You can lose some data. You can have the program crash like what just happened here. And any one of those things can possibly happen. It's totally unpredictable when you just start trashing random memory with a buffer overflow. You really want to avoid that. Little side story. Okay, this is my most embarrassing programming story, frankly. When I was college age, I was home on vacation at one point. I was working on my parents' desktop computer, and I was making a little video game, and I made a little mistake. I made a little bit of a mistake, and there was a buffer overflow, and I destroyed the computer. I actually fried the hard drive. The hard drive stopped working. It never worked again. And I was so ashamed, but my parents had to go buy a new computer because it was actually just destroyed from buffer overflow. Destroyed something in the hard drive mechanism, apparently, just from a tiny little mistake. Now, I don't think that that's something that's going to happen nowadays because the operating systems have a lot more security built in. Like right here, Windows stepped in and really stopped this before things got too bad. So I don't think it's going to be quite that bad, but I would really recommend avoiding buffer overflows as much as possible because, really bad things can possibly happen. Hopefully not literally destroy hardware, but that actually has happened to me in the past. So hopefully never again. And I'm so glad our computers are better than they used to be. And I hope you never have to confront something quite that bad. But when we say buffer overflows are bad, it can possibly, I was so ashamed by that, but I actually have literally permanently destroyed a computer because of this problem. So I am going to get this program off my screen. Hopefully I never run it again. And I'm going to be happy to go back to normal safe programs for the rest of the course. Okay, so I hope you're convinced that buffer overflows are really bad and you really want to be on the lookout to avoid them. Now, the most common way that happens is what's called an off by 1 error, is you can have code that's almost correct, it's just off by 1, and that one tiny little change can make a buffer overflow and can possibly crash your program or your computer. So an off by 1 error is what happens when you use array subscripts that are just off by 1. Remember, if I make an array size 10, the array starts at 0 and it ends at 9. And it's very possible for beginning programmers to forget that, and just being off by 1, buffer overflow, huge catastrophe, frankly. So this can happen when you start subscripts at 1 instead of 0. Here's a slice of code here. It almost looks correct. It looks so close to what we normally do. You've got a named label here for the size constant, okay. You're making a numbers array size 100, that makes sense. And then you have this for loop. And this for loop is actually going to iterate 100 times. Okay. The problem is it starts at 1. Actually, that's not a big problem, although you missed the 0. The real problem is that the loop controller says count less than or equal to size. So it's going to go 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 97, 98, 99, and then 100. And the problem is 100 isn't actually a subscript in your array. It stops at 99. So on the very last item, like it worked 99 times if you run this code. But on the very last item, count becomes 0, and you try to assign a number to numbers sub 100, and that's a buffer overflow. And maybe your program crashes or something crazy happens. So be on the lookout for that and try to be very, very careful with your for loop controllers, because even just being off by 1 single number can be catastrophic. All right, enough of that. So my students will get together and we'll do this lab 7.2. And remember, this video started talking about what are strings? Well, they're really just arrays of characters, particularly if you use the old school C strings. You will have an array of characters in this lab, and that's how you're going to store some students' names. This program should let the user fill in a set of test scores for each of several students, plus their names in a C string, handle their name, call functions to compute the average and the letter grade for each with several test scores there. So once again, getting some practice with arrays, passing an array into a function, computing the average, returning it. We said we were going to do that a lot. So here that's popping up in this lab. Again, another good area for practice with our various array algorithms, including storing names in arrays of characters, which is all strings really are. So when we come back next time, there's one last thing we're going to talk about in Chapter 7 with arrays, and that's the issue of multi-dimensional arrays. So far, all the arrays we've made have just been one single block of memory from start to finish, kind of in a line anytime we visually displayed it. But you don't have to do that. You can make what's called a multi-dimensional array. Like, the first thing that comes to my mind is a mathematical matrix, if you know what that is, a grid of numbers. And that's not just one line. It's got a number of rows, it's got a number of columns, and now this has 2 dimensions, right? Those 2 factors, the rows and the columns, are how you size a matrix. This would have 2 dimensions instead of just 1. So that's the issue of multi-dimensional arrays, and we'll talk about that next time. Hopefully that sounds interesting, and I'll see you for that.